Hello everyone, I'm Ryan Allen, and this is my Practicum 1 Capstone project for Regis University. I'll be doing a clustering and analysis of terrorist attacks. I'll be using the Global Terrorism Database, and I'll perform an exploratory data analysis. After I do that, I will use hierarchy and k-means clustering to find distinct groupings and clusters within the data, and then using those distinct clusters, I'll perform exploratory data analysis, looking for any defining characteristics or features. The Global Terrorism Database is maintained by the Study of Terrorism and Responses to Terrorism, also known as START, at the University of Maryland. They collected data from 1970 up until 2017. It's mostly categorical data where each row represents one terrorist attack. There's over 130 columns and 180 observations. Over on the right-hand side are the number of missing data points per column. So you can see that I have a lot of data values that are missing for a lot of columns. What I ended up doing for my clustering was filtering any column that had more than 25% missing data. With my exploratory data analysis, it's really a twofold process. One, I want to show any key insights and highlight distinct things about the data set itself. And then the second one is I want to be able to draw some comparisons to the overall data and what my clustering looks like. So here we're looking at our attacks ranked by region, and we see that bombings and explosions were the #1 attack type across all regions. We don't see a ton of variability as we move left to right. We see that some of our attack types will move maybe 1 to 2 rankings, but we don't have a lot of movement. We want to do the same thing with our weapon types by region. So we see that explosives is the #1 weapon type by each region, with the exception of South and Central America, where that becomes firearms. With this chart, we see that we have a little bit more variability as we move left to right. Here we get to see that Iraq had the most attacks with over 24,000, which is 10,000 more than its second counterpart, which was Pakistan. We also get to see that bombings and explosions were the most common attack type, which we already knew, but here we get to see the proportion in that bombings and explosions had twice as many occurrences as armed assault. And then down in the bottom right, we see our most common weapon types, which we already knew to be explosives and firearms, but here we get to see how prevalent those two weapon types were compared to all the other weapons. I wanted to look at the suicide rates by region. When I think of terrorism, I usually think of suicide attacks, and so I wanted to know how prevalent were suicide attacks within each region. And what I found is that there weren't actually a high number or percentage of suicide attacks. So we see that the Middle East and North Africa had the most at 7.5%, and then it stair steps its way down until you hit North America, and below that where we see that suicide attacks represent less than 0.5% of all attacks. Here we have two time-based charts that are looking at the number of attacks over time. So the one in the upper right is total number of attacks. And what we see is that the number of attacks per year stayed fairly consistent up until right around 2012. And then we see that it spikes in 2014 with over 16,000 attacks. We have an average number of attacks per year of around 3,800. The bottom left chart is looking at what I called extreme attacks. So extreme attacks were a personal designation that I came up with, and it's any attack that kills more than 100 people. We see that it has a similar trend, and then it stays fairly consistent up until right around 2014, where we have that spike, and there were 29 deadly attacks. Before I could move on to my clustering, I had to first impute all of my missing values and then perform a principal component analysis to figure out which of my columns and features contributed the most of my variance. What I ultimately found was that 28 features explained almost 100% of the variance of my data. So moving forward, I chose those 28 columns. To find the best number of clusters to use, I use 3 different methods. One is the gap statistic, which is the within cluster sum of squares. It's a metric of error. And when I did that, it came up with 8 clusters would be the best. After that, I used the package mbclust, which uses a variety of methods, but ultimately it casts votes on what it thinks is the best number of clusters. So the #1 voted cluster grouping was 3, and then the second best was 8. So then the last thing I did was looking at this dendrogram over here on the right. I visually tried to figure out where I could cut it horizontally to give me the 3 groups, and also where I could cut it to give me 8 groups. And ultimately, I decided on 8 clusters. I started with my k-means clustering, so I picked 8 centers and then I did 20 random starts. So how k-means clustering works is it picks 8 random center points, and at that point it assigns all the different data values to those centers. And then within each one of those clusters, it finds the center of that cluster. And then with those new centers, it then assigns all the points to the closest center point. And it keeps repeating this process until all of the cluster assignments stop changing. Once they stop changing, you have your clusters. So here is a chart of the clusters that I have looking at our dimension 1 and dimension 2 of our principal component analysis. I wanted to show this chart because it helps show that we do have some defining characteristics of our clusters that I will point out more as we go along. For the hierarchical clustering, I used Euclidean distance for my data. And then once I had that Euclidean distance, I put that into a complete linkage method. And so what that complete linkage method is doing is it's finding the distance between the pairs of a cluster and their members. And then it finds the distance between all the members of that one cluster and another. And then the maximum number is reported as the dissimilarity. And then clusters that have the smallest dissimilarity are then grouped. And this process repeats over and over until you're left with one cluster. There's 2 different ways that you can measure the strength of clustering. So one is the external measures. So for this one, I was worried that my clusters were going to follow along the lines of my categorical variables. So to test against that, I use what's called the RAND statistic. So the RAND statistic looks at any agreement or disagreement between clusters, assigned clusters, and then any groupings in the data. So the RAND statistic ranges from -1, which is no agreement, to +1, which is total agreement. And what I found with the region, my weapon type, and attack type was that all of them have a RAND statistic of 0, suggesting that there was really no similarity or dissimilarity between them, which is basically what I was hoping for. The next one is the internal measure, which is the silhouette coefficient. So this measures the average distance between clusters. This one also ranges from -1 to 1, where 1 represents a high value or a well-matched value between the cluster and the point, and a -1 meaning that a point has been mislabeled. I had no negative coefficients, which means none of my points had been incorrectly labeled, and I had an average silhouette coefficient of 0.56. On my exploratory analysis of my clusters, I'm going to be trying to show you some defining characteristics and features of each one of the clusters. So here we're looking at the distribution of regions, and we see that cluster number 7 has a very distinct distribution in that it's centered primarily on the Central and South America region. We also see that cluster number 3 has a different median than all of our other clusters, and that it is centered around region number 6. I'm showing this chart not necessarily because I think it is visually stunning, but because I think it has a key insight. So this one is looking at the number of extreme attacks and percentage of extreme attacks. And what I found was that cluster number 4 actually has all of my extreme attacks. And it also represents more than 10% of the attacks within cluster number 4. So it's going to kind of be a theme moving forward. You'll see that cluster number 4 is by far my deadliest cluster. Here we have all the different attack types by each cluster. So for this one, what I really want you to focus on is down in the bottom right, where we see cluster number 8. Cluster number 8 has a very different attack type makeup than everyone else, where it's focused on facility and infrastructure attacks, hostage taking, and then unknowns. All the other ones are fairly similar in that they all have high numbers of armed assault, assassination, and then bombings and explosions. This is my favorite chart when I'm looking at my clusters because I think it really highlights some of the key differences. So clusters 1 and 4, they have the smallest amount of numbers actually within the cluster. But what we see is that number 4 has a much higher death count, especially the number 1. And that's because number 4 has all of our extreme attacks. Also, the distribution of number 1 is different than most of our other distributions and is different than the original data set. Clusters 2 and 3 to me also show some unique differences. So cluster 2 doesn't have any data values before 1995, it looks like, and cluster 3 doesn't have any data values after 1995. When you look at clusters 4, 5, and 6, we see that they all have, and I guess cluster 8 as well, we see that they have a similar distribution makeup as the original data set, where the attack types And the deaths stay fairly consistent up until right around that 2012, 13 range, and then we see spikes. And then finally, we have cluster number 7 that has a totally different distribution than everyone else, where it's centered on 1980 or early 1980s, where we see that spike in deaths. Looking at the suicides by cluster, we see that cluster number 6 has the most suicide attacks. But we also know that not each one of our clusters has the same number of data points in it. So I was curious what the percentage of suicide attacks look like. So I colored each one of those bars by the percent. And here we see that our cluster number 4, which is our deadliest cluster, not only was it the deadliest, but it also has the highest percentage of suicide attacks, where it is sitting at just over 40% of the attacks being suicides. This is looking at the top ranked weapon types for each cluster. A couple things I want to highlight about this one. This to me shows that cluster 8, one of its defining characteristics is weapon type because it has a different makeup than everyone else. But also it shows me that our most popular or highest rank weapon types for each cluster probably is not a defining characteristic, but as we get below rank 4, we see that our makeup starts to change. So that leads me to believe that perhaps some of our lower ranking weapon types could actually be defining characteristics of some of our clusters. This chart is looking at the target types of each one of the attacks by cluster. I included this one because it's kind of a messy plot. It's visually not easy to look at, and it's not easy to get any insights, which I think is valuable when we're talking about clusters. What it leads me to believe is that our target type is not really a defining characteristic for any one of our clusters. If it was, we would see similarities across the board, and then one cluster would be different. But this one, everybody is different. As I think back about my project, there's a couple things that I would perhaps do differently or spend more time on. One thing that was concerning to me was that my gap statistic in my MBClust package disagreed on the best number of clusters. So I would spend more time trying to figure out what those differences might be. Probably what I would do is do an analysis with 3 clusters and then do one with 8 clusters and then compare some of those internal and external measures. I think you can always spend more time on imputation methods, trying to find better ways to fill in those missing values, especially with categorical information. With the data set size, I ran into computing power issues, and so I ended up having to sample with replacement on my data set instead of using the whole thing. But I'd be curious to know if there's better ways of handling that, or perhaps doing different iterations with those sampling with replacement. And then finally, those cluster strengths. There were many other internal measures for comparing cluster strengths that I think you could spend more time on. Looking ahead for some future work and considerations, I think one thing you could do is do some further analysis on this current database and the current clusters. My assumption is that there are some other defining characteristics that I haven't found, that using some creativity and thinking outside the box, you'd be able to find some of those. I also think it'd be valuable and insightful to look at this database compared to other time-based data sets, such as like stock market data. I think it's pretty well known that terrorist attacks inform the stock market, but I'm curious if we could actually flip that and if the stock market could be used as a predictor for terrorist attacks or perhaps extreme terrorist attacks. The other thing I would look at is text analytics and natural language processing. So what I would do is I would find a specific region in the Global Terrorism Database, and then I would use that same region to scrape Twitter to find tweets from that region and see if maybe perhaps sentiment analysis or other text analysis to see if I could use that as a predictor for terrorism attacks. So instead of looking at what do tweets look like after the attack, I would look at what did the tweets look like before the attack happened and see if we could use that as a predictor. Thank you everyone for listening. Just as a quick recap and conclusion, we looked at the Global Terrorism Database. We were able to cluster that database and then do some exploratory data analysis to find some unique features and characteristics of each one of those clusters. I want to thank all of these resources that I used throughout the project as they were instrumental in giving me ideas for my k-means clustering, principal component analysis, my ggplots. So thank you, and I hope you have a good rest of your day.